Welcome back to another episode of PEEPanEIP and EIP dedicated series, where we discuss an Ethereum improvement proposal and understand how it is going to improve the Ethereum ecosystem. My name is Pooja Ranjan and I'm your host for today's episode on improvement proposal for removal of refunds. Berlin upgrade was deployed last week. With that done, the focus of Ethereum client developers shifted to the upcoming upgrade London. The EIP-3403 partial removal of refund is one of the top list proposals to be seen in London upgrade, alongside with the EIP-1559, the fee market change, EIP-3198, the base fee opcode, and EIP-3238, that is difficulty bomb delay. According to the simple summary provided in the proposal, this proposes to remove gas refund for self-destruct and restrict gas refund for SSTORE to one specific case. To talk more about the proposal, we have got none other than the co-authors of the proposal, Vitalik Buterin and Martin Swende. Thank you for joining us.
Thank you for the introduction, Pooja.
So Vitalik and Martin have been on our show earlier to talk about EIP-2929 and EIP-2930. They both are deployed on the mainnet with Berlin. And as I understand, EIP-2929 is also required for test cases for this proposal that we are going to talk today. So without further delay, let me pass it over to the co-authors.
Thank you. So to start off, I guess we'll talk a bit about what the goals of EIP-3403 are. So I think the most important goal is to basically remove some of the harmful effects that we've been seeing as a result of gas refunds. So the main two effects that we saw there, or that we're seeing right now, one is the gas and storage size that is being wasted on gas tokens. So basically gas tokens essentially use storage as a battery, and they just consume 5,000 gas or 20,000, or they consume a full cycle of a gas token consumes at least 5,000 gas, and this ends up taking space away from transactions, and it also increases the size of the state that nodes need to store. And the second one is block size variance. Basically, if you take into account refunds, a block with a gas limit of 12.5 million can consume actually up to 25 million gas on execution. Basically, gas refunds are capped at 50%. And so if you have a lot of gas tokens, then for every transaction, you can just use the gas token to refund up to half of the gas, and then you can include even more transactions. Now, unlike the variants in EIP-1559, where blocks can go up to 2x the target, in EIP-1559, a spike of 2x could only go up to about 5 minutes. After 5 minutes, the gas price would, or the base fee would increase by a factor of 15, so it would become economically unviable to continue. But with refunds, an attacker can basically continue a 2x spike in gas usage for basically as long as they want, and as long as they have money to pay for gas tokens with. Martin, anything
to add? Maybe you're mentioning this later. I don't really recall. But one thing. So there's been talk about should not increase the gas limit. And it's kind of like if the gas limit is raised, or whatever the gas limit is, there is no incentive for miners to not fill slack space with minting gas tokens. So whatever we set a gas limit to, the gas limit will be filled by gas tokens by like rational miners. Which is kind of shows this kind of perverse incentive that is currently where you're always incentivized to mine. If you have nothing better to do, you're incentivized to bloat the state and hope that someone buys it from you later. And that's one of the effects that that is being addressed here.
Right. I guess like sort of one game theoretic nuance to add to that is that if we agree that EIP-3403 or something similar is going in, then the incentive to create new gas tokens would go away even before the EIP is actually included, right? Because like there's no point in minting them if their price starts approaching zero, because they all become worthless at some known date, like a month or so in the future.
Yes, and it's also worth noting that, I mean, gas tokens are a utility token, and they derive their value because they can actually be used and have an actual value, whatever which depends on the gas price of the blocks. But until the day that we actually switch over, I mean, they won't be worthless, but they can actually, the ones that currently exist can be used and basically cashed out. But yeah, if there is continued minting and too much minting, that making it so that that there still are gas tokens left when this change happens, then that would drop to zero.
What would drop to zero exactly?
The value of gas tokens after a hard fork which implements this change.
So is this trying to like obsolete gas tokens basically?
That's goal number one in on this slide. So yes.
Am I correct in understanding that the problem with having a extended like 2x or something like that is state bloat, as in the gas limit is where it is in order to keep some sort of cap on the amount of state that's happening in each block? Is that the primary problem?
So no, it's actually not state bloat. The thing with state bloat is that state bloat is dependent on kind of long-term average usage and not short-term spikes. And both EIP-1559 and gas tokens, actually, both of them have this property that they only can create spikes. They cannot affect long-term usage. In the case of gas tokens, it's because it costs 20,000 gas to create one, and then you get a refund of 15,000. So this is orthogonal to the storage issue. This is more about, like, basically imagine a short-term DOS attack where an attacker discovers some technique that we don't know about for making blocks that take 10 times longer than usual to process. And then on top of that, they burn a bunch of gas tokens, and then they create blocks that would say take, I don't know, like 15 seconds to process instead of 7.5. And like with DOS attacks, like it's not a binary, it's a spectrum. And then the longer they take though, then, you know, instead of a 51% attack, you could do a 31% attack, for example. So it's at least, like, to me, the variance issue like is about DOS, and I guess it also is about low powered clients potentially like having a well, like basically we would rather low powered clients be able to keep up at all than low powered clients keeping up excellently on Mondays and not and getting 3 hours behind on Tuesdays. So those two concerns.
Yeah. And one more thing now, we're talking about gas tokens. So as far as I know, and please correct me if I'm wrong, the original gas token was an idea devised by Phil Diane a couple of years ago, and they published this like gas token, kind of like an exploit. And the original gas token write-up says that basically this is exploiting a quirk in the Ethereum protocol specification. And we've implemented this just to kind of demonstrate this quirky behavior, and we kind of expect that the protocol development at some point will remove this quirk, which we hereby have demonstrated. And I think that kind of nuance got lost, and it was kind of became considered to be an actual like feature. Yeah.
Okay. So secondary goals, so basically of EIP-3403. One is to just be maximally simple. So it's not a kind of nirvana perfect solution. And like one reason why is, you know, we want to focus on the merge, and that becomes harder if, you know, weeks of core development needs to be redirected on some more complicated transition that sort of completely reorgs things and adds like 5 different clauses. And also, this is a short-term fix anyway. So basically, state expiry. So or part of the solution to the state problems is going to sort of re-architect storage in a different way, and I'll talk about that in later slides. And also to retain as many of the beneficial aspects of refunds as possible. So to maintain the good, as many as we can of the good properties of what of incentivizing clearing, storage, and so forth. So the spec, fairly simple. Remove self-destruct refunds completely. Another sort of kind of future note is that it's looking likely that it'll make sense to just turn off destruction, kind of the destruction functionality of self-destruct completely when we add Virtual trees. That's basically just because it gives us more freedom to create kind of better state storage structures when we keep the invariance that there isn't one opcode that has the ability to like potentially affect tens of thousands of slots at the same time. But that's another discussion. So EIP-3403 will just get rid of the refunds, and then removing SSTORE refunds in all cases except for one, right? And that case is basically this. So 0 equals due equals original does not equal to current, or in English, basically, the refund happens only when a storage slot that was 0 at the start of the transaction but became non-zero is set back to 0 again. And in that one case, the refund actually goes up from 50,000 to 19,000, and in the other cases, it's there's no refund anymore.
Is there an obvious situation where that would happen, where there's kind of this? If I'm understanding right, it's kind of like an intermediate state. It's 0 goes up, goes back down to 0. Is that correct?
Yes, and there are such cases, those are 2 slides in the future.
Excellent.
Okay. So this is just nice properties that EIP-3403 has. So some kind of invariance that we have once the EIP exists. So one of them is that you note that every refund of 19,000, it gets paired with a corresponding 20,000 cost for setting that same storage slot for 0 to non-zero. So what I mean by this is that, for example, if you have this pattern of a contract storage changing its value, it goes from 0 to 5 to 0 to 7 to 9 to 0. In red here, the 0 to 5 and the 0 to 7, that's the 20,000 costs. So for setting the storage slot from 0 to non-zero, and then the green 5 to 0 and 9 to 0, that's setting non-zero to 0. So in this example, you would get your 38,000 gas refunded from the 2 greens, but the 2 greens just have to have these 2 corresponding reds, which cost 40,000 gas to actually set the storage slot to non-zero. So the result of this is that the gas spent, well, what I call gas spent on execution, cannot exceed the gas limit at all, right? Like basically, and what I mean by this is that the 20,000 that's being spent on 0 to non-zero doesn't really count as execution, because the reason why this cost is 20,000 in the first place is because it's 5,000 for the updating the state tree and 15,000 for growing the state size. But the state size growth gets reverted because we're going back to 0. And the state tree update is also reverted, because if it starts as 0 and ends at 0, then like the node doesn't even actually have to do any database writes to update that particular value, right? So even though the cost of 20,000 gets refunded, the effort that clients would have needed to spend as a result of the 20,000 also gets reverted as well, if that makes sense. So like basically what this means is that the refund, like there's no way to use this to create a block that has 25 million gas available for DOS attacks. And also, because every refund is paired with this corresponding gas cost on the same storage slot, you can't clear some storage slots to fill other storage slots. So you can't use storage slots as a battery. And so like basically gas tokens, kind of the whole class of them can't work anymore. Martin, anything more to add?
Yeah, regarding that that little feature about about keeping the same storage slot. So currently there's this kind of quirky thing where you can clear one storage slot and you set another storage slot and you get the refund for the one you cleared and you pay a price for the one you set. And totaling out that they kind of somewhat cancel each other out. And from the perspective of the actual node that is executing this code, that doesn't actually map to the resources expended, because what the node needs to do is do two writes. It doesn't need to do less work than if the set to 0 was not performed, but it needs to do two writes, and it doesn't matter if one is writing a 0. I mean, deleting something from a try or not, it's still two writes. So I think this model of paying for it actually maps more accurately to the resource expenditure of the executing node.
Okay. So kind of concrete benefits kept by EIP-3403. So one common contract flow is a storage slot going from 0 to non-zero to 0. And two use cases of this. One is a token approve and send. And so you have a token you want to set, or he wants to use a token to pay for something. And so you first approve the token, and then you immediately call the contract that's going to be taking the token payment, and then the contract calls the ERC20 and does and claims the approved balance. And the storage slot containing the approved balance would actually go from 0 to non-zero to 0. Now, so that's one use case. And with EIP-3074, this is likely to become more important because whenever we end up adding either EIP-3074 or something similar, or we move to smart contract wallets without any EIP, any one of those, then you actually, there are currently a lot of cases where you have users send two transactions, the first transaction to do an approve and the second transaction to do a send. And with with any of those EIPs, that would be able to go down to one transaction, which would improve UX. It would remove unnecessary gas usage. It would have some nice consequences, but it would also create the 0 to non-zero to 0 pattern. And the second is anti-reentrancy locks. So this is basically a contract setting a flag when it makes an a contract setting a flag in its own storage when it makes an external call, so that if that contract calls some other contract and then that contract turns out to be an attacker and then it calls the original contract again, the contract detects that its flag is set and it will reject that internal call. So if A calls B calls A, then in the inner call, A had already set the flag, and so that inner call would get rejected. And then at the end of the transaction, that flag would be set back to 0. So in both cases, you have 0 to non-zero to 0. And the lovely thing about EIP-3403 is that it actually makes this cheaper, right? So before the 20,000 cost for setting 0 to non-zero, and then 15,000 refunds for setting non-zero back to 0, so 5,000 total. And this does not include storage cold read costs. It might also be off by like either 100 or 800, I forget, but it's approximately this amount, right? After EIP-3403, 20,000 cost and 19,000 refund. Basically, we can safely increase the refund because the refund only applies in the case where you're resetting it back to the 0 that was there originally, and so you actually are canceling out the storage on disk. And so the total cost becomes 1,000, also not including storage reading costs. And there are some contracts that do 1 to 2 to 1 instead of doing 0 to 1 to 0, but after EIP-3403, 1 to 2 to 1 will actually cost more than 0 to 1 to 0. So there, to some extent, it does kind of incentivize the better workflow. Anything to add there?
No.
Oh, okay. So weaknesses of EIP-3403. So this is the one that I think William Morris mentioned on some opcodes calls. It creates a possible incentive to leave behind one subunit when you're emptying out tokens. So say I have 500 units of Wraps Doge and I want to send my Wraps Doge somewhere else. Then instead of sending the if I know that there is even the slightest chance I will ever want to receive the more Wraps Doge in the future, instead of sending all 500 Wraps Doge away, I would send, say, 499.99999. And then in the Wraps Doge contract, the RC20 balance, you would have 0.00001 remaining. And like, you don't really care about 0.00001 Doge, but what this gives you is if you ever receive some Wraps Doge in the future, then instead of that costing you 22,300 gas for filling a new storage slot, it will cost you, oh, actually, this should be only saving 15,000. I think it'll save you, yeah, it'll cost you 5,000. And so it'll save you about 17,300 gas. So the reason not to do this today is that if you send away all your Doge, you do get a 15,000 refund. So you would only want to leave one subunit behind if you're really sure that your balance is going to go back up above zero. But with EIP-3403, this incentive goes away. And so there is more of an incentive than before to do this, like leaving one subunit behind trick. If we really want, there's this one kind of like a possible mitigation, which is if the original value was not zero and the current value was not zero, and the new value is zero, then you charge for 3,000 instead of 5,000. So you do have a bit of a gas cost reduction for clearing. And this kind of improves things slightly, except one concern is that it does increase the invariant on the maximum number of storage slots that you can change in a block. And that's also one of the invariants that I think theoretically we would like to just be able to clamp down on, especially as we start talking about going into virtual trees and so forth. So those are, I think, like the key weaknesses that other people have pointed out. But one thing to remember also is that, like, I think if you're building a new application, then like redesigning everything around these rules doesn't really make too much sense, because in the long term, for doing state expiry is expected to kind of change the calculation again. And the reason is basically that state expiry in whatever format is likely to require us to store 0 and empty as distinct values, right? So if a contract goes 0 to 1 to 0 to 0, and then it goes 0 to 1 to 0 again, after the first time it goes 0 to 1 to 0, like you, instead of the storage being empty, you would actually have a 0 saved in the storage tree. And the reason for why we need to do this is because to determine the state of an account in a state expiry model, you basically have to kind of look for the most recent epoch in which the account is in the state, right? So either the account is in the current state tree or the account is in some expired region. And you have to figure out its state, you have to kind of start with the most recent one and walk backwards. Now, a storage slot being empty basically means nothing happened here, so you have to keep looking backwards. And 0 means something different. 0 means in this particular epoch, the account actually was set to 0, and so the value is 0 and you can stop looking, right? And so what this means is that non-0 to 0 in the long term is not even going to be clearing anymore, right? So the concept of active clearing is likely to not exist at all, except basically what you'll have instead is, as state expires, state objects that people no longer care about kind of get cleared by default, right? And so like 0 to non-zero to 0 to non-zero across multiple transactions would just cost, it's not going to cost 20,000 plus 5,000 plus 20,000. It'll just cost 20,000 plus 5,000 plus 5,000. So in the longer term, like basically, yeah, you don't actually, there's not going to be a lasting benefit from, leaving 0.00001 Wraps Doge behind in your account in case you want to get more. There's not going to be definitely not going to be any benefit in using 1 to 2 to 1 for your mutex locks instead of 0 to 1 to 0. And so like designing a long-term application around kind of quirks in EIP-3403 rules is just probably a bad idea for application developers.
So there's one thing I would like to go back to, because you said earlier that 2929 actually makes the case cheaper of 010. And I think after Berlin, that's not actually, so Berlin will only, and I'm looking at the actual EIP now, EIP-3403, where we have the test cases. So 010 in Berlin costs only 212 effectively, because there's the refund.
Right, I see, hold on. Is that because the 0 to 1 costs only 15,000 or?
It totals up to a refund of 19,900.
Oh, I see. Berlin. Okay, so Berlin already adds adds a higher refund. Okay, then. Then no, and if that's true, then that's my mistake. Then this should just read as just EIP-3403 preserves the property that this is cheaper.
Yes, and also the I think, if I'm not mistaken, that the 3403 costs are still cheaper than before Berlin.
Right.
So Berlin made certain things cheaper, and that's like temporary. We made it cheaper, and 3403 would raise it a bit again. So the effective gas would be 1,112 without particular code used. Just basically 900 gas effectively. That's the difference.
Right. Okay. So so with the EIP-3403, then the token of proven send and anti-reentrancy locks can just continue to be cheap, and 010 continues to be a better pattern than 1 to 2 to 1 for storage slots. Okay.
Yes.
Good to know. Okay. So basically, kind of for developers, or 0 to non-zero patterns will continue to be cheap. Using 1 to mean 0 instead of 0 to mean cleared is this kind of bit like this one incentive weakness that EIP-3403 does introduce, but it may be cheaper in the short term. But like after state expiry, which could come, maybe 1 to 2 years in the future, there's not going to be benefits from doing this. And these kinds of patterns, like they combine well with the EIP-3074 for if you want to do a proven send. So basically developers would not have to do too much. And then the other takeaway is basically that like the most common use cases of a refund, which is just making sure that these use cases that basically use storage as temporary memory and then set it back to what it was, are not going to actually become more expensive than they were. But the benefits from this EIP is basically that it does kind of remove these fairly big incentive misalignments from the protocol, where first you remove this ability to basically use storage slots as a battery and kind of send these transactions that take up a large amount of gas space, so that you can give yourself refunds later, and at the same time removing block size variance. So that's it. It's actually a fairly simple EIP.
So one of my questions would be what this is kind of, I guess, a little bit tangential, but why are the SLOAD and SSTORE opcodes so expensive?
Okay, this is an important question. So SLOAD, basically they're expensive because IO operations, so reading and writing to disk, are expensive. And in fact, the worst DOS attacks we had against Ethereum, and even the worst ones that have been found academically since then, have to do with basically just spamming access to lots of accounts and storage slots. And so in the case of SLOAD, that's disk reads, and in the case of SSTORE, the cost of 5,000 justifies the fact that you have to store a bunch of values to the database. You also have to basically load up everything along the tree in order to adjust the Merkle branches and figure out the new state root. If you have an archive node, then the size of an archive node gets bigger. And then the cost of 15,000 is to account for the size of storage being bigger. So that's today. And then in the future, even when we go into doing more statelessness, witness generation and witness updating are still among the more expensive operations that we're going to have, and so there's still a strong need to try to kind of really clamp down and have fairly tight limits on how many storage operations we can have in a block. So for example, we've been working on Verkle trees kind of quietly in the past month, and we've been targeting being able to make 5,000 storage key updates to a Verkle tree in something like under half a second. And so that amount of time is acceptable, and it's even acceptable, if you increase a gas limit and on top of that you attack the tree, there's this a fairly big margin of error. But if the cost of storage was or continued to be what it was in, say, 2015, then instead of the limit being 5,000, the limit would be 500,000, and it would just making a witness structure would be impossible. So basically both short-term and long-term storage storage reads and storage writes are expensive for several reasons.
Have you considered not removing 0 elements from the state trie after this EIP? Because it's easy to say that in the long term, developers shouldn't do this thing where they have a new sentinel value for 0, but in reality, I think it's very likely that they will do that.
I mean, I think the challenge with that is that is what we would call a deeper change to the EVM, and so it would require testing. It would potentially require some clients to re-architect themselves in a significant way. So the burden of the EIP would be higher, whereas here the EIP is basically only a few lines of code, and so it's not deep in any way, and that just makes it safer to actually implement.
I guess, yeah, maybe it's a much bigger change than, it sounds when I say it's simple, but.
No, it's a humongous change. If I understood you correctly, that we would actually store 0, which would affect the try.
Yeah.
For one thing, we could never do it. It would have to be whenever you store a 0, it modifies the try. Yeah, it would be very large change. And basically, because you wouldn't know when you do a fast sync and you get the state back, it would be difficult to know, was this account encoded in the old style format or the new style format? Yeah, there are lots of quirky edge cases in this area, I think.
Yeah. It just seems unfortunate because I'm almost certain that in this period of time between when this EIP goes live and when, we have some state expiry mechanism, that developers will have a new sentinel value for 0, and then there will again be a transition back to using 0. And so this is a bad UX. This will be a bad UX for users when this EIP launches, because their contracts will become more expensive. and it will be a bad
Why-
UX.
Why do you think it will? They have another sentinel value right
There
now.
is, sorry, right now another sentinel value.
Yeah, it sounded like you.
I guess the argument would be like someone making a new ERC-20 contract would just decide that, we'll just offset all the balances by 45. And then if a balance and then we'll just pretend that 45 means 0. And if you see if you have a new account, then it'll just be immediate. The 0 would also be recognized as 0. But if a balance gets set to 0, the storage slot would be set to 45. And that would be cheaper in the cases where you go kind of out and in, or where a balance becomes 0 but then becomes non-zero again. But yeah, right. So I went back to this slide. So if we decide this problem is significant, one possible mitigation is to also just add the second rule where instead of a refund, basically, if a storage slot is set from 0 to non-zero, you charge a lower, basically 3,000 gas instead of 5,000. Or we could even say charge 5,000 and do a refund of 5,000. So you would still have a little bit of incentive to do the 0 as, or to pretend a non-zero value is 0 if you're certain that it'll become non-zero again. But at least in those cases, like ERC-20 token balances, for example, where you're not sure, the incentive would continue to be pretty strongly toward using the 0 as a 0.
Yeah, that makes sense. I definitely think that would be an important thing. I really don't like that as is, this would push developers to use a different value for 0, because it's not like consensus code. It's not simple to upgrade those things. And as we transition, there's always going to be contracts that are left behind using the old things.
So I'm kind of confused on how this works here. Kind of from a really basic level. So what exactly is the subunit thing going on here?
Oh, sorry. A subunit is the equivalent of a way, but for an ERC-20 token. So if you have wrapped Doge, then if you have 42 wrapped Doge, then your balance is saved as 42,000,000, and then there might be 18 zeros or 16 zeros. I don't even know how many zeros they use. So you would just leave behind the tiniest amount of this is if you want to kind of exploit existing ERC-20 contracts, then you would leave one subunit behind, and then if you ever wants to receive more coins, then you would just use that same or in that same account, then you would have to pay less gas.
Yeah, and I mean another in the other example. So if you have a variable that you use as a mutex to ensure that you don't get no one does reentrancy attacks against you, you have the option to use this mutex variable by default set to 1, and whenever you make an external call, you set it to 2, and then before you leave, you set it back to 1. That's 1, 2, 1. Or the other pattern is to have it at 0, set it to 1, and set it back to 0. That's the corresponding case, which we're kind of talking about. Does that answer the question?
I'm still not super clear on it, but I think that maybe this is something I have to study. But
basically,
it's like
as a
and
developer,
cents.
is it better for me as a developer to leave this value that I'm going to use to leave it at not 0, or is it better to leave it at 0? Depending on if I want to use it in the future. Because it because of how, and this is affected by how refunds work and how much it costs to set something that was 0 to non-zero. So it's kind of what we would hope to avoid is having some an incentive where developers just leave stuff. Although I personally think that that problem is kind of small compared to this other problem of the gas tokens.
So I guess I'll ask one more question to try to clarify. If I don't get it, then it's okay. But so is the idea that like you enter a contract, which is kind of like an object-oriented programming or whatever, it's like an instance, and then you're saying that it's best to leave like behind changes that were made to then be reaccessed if you go back into the contract? Is that what you mean?
No, not quite. More like when you enter this contract, if this contract during its execution wants to use a temporary variable, let's say it will always use a temporary variable. Now, is it better gas-wise, consumption-wise, to have that variable already initialized and leave it initialized for the next time this method gets invoked? Or is it better to uninitialize it and set it back to 0?
And so are you saying that in order to initialize something, you have to use like the storage, and then in order to use it like for temporary, then you would use memory? Is there like a difference?
No, we're talking about storage only.
Okay. That makes
And when I say temporary, I mean like it's used during this transaction, but it doesn't actually convey something. You don't actually need the value at the next execution. You just want to be able to use storage slot.
Oh, that actually makes sense, because I have seen in some Solidity code people consistently instantiate before a method. So that makes sense.
Right. Like one kind of development nuance here is that Ethereum clients, they have a cache, right? And like when you do an SSTORE, they don't like go in and start going into the database and mucking around with the Patricia tree immediately. They just save the updates in the cache. And then at the end of the transaction, or sometimes even at the end of the block, they take all of the updates and or all of the actual updates and then process them all in one batch. And so if you basically use storage in a way where at the beginning of a transaction, it starts at 0 and then you change it to something else, and then you change it back to 0, like the part of the client that actually does the kind of committing, like it sees that the new value is the same as the original value. And so it doesn't actually do any writing on disk, and it doesn't actually do any like editing of the Patricia tree. So you're basically using storage as a kind of memory that just basically as a kind of memory that can be kind of shared between different execution contexts. So like between a parent call and a child call, for example.
Oh, that makes sense. Yeah. Thank you for explaining. I have one follow-up question to that then, to clarify on what exactly storage is. And is that like, can you access like a storage variable that was made like at Genesis? Like, is all of that just stored?
By Genesis, you mean the time that when a contract is created?
No, I mean like from like block 0.
But there were no contracts on the Ethereum blockchain until block something like 40,000.
Okay, but since then, but because my
Yeah,
point, like,
right. But if somebody created a contract in September 2015, and that contract had 2 functions, one to set a storage slot and one to read it, and somebody called the function to set the storage slot, and then somebody went and made a transaction to call the function to read it today, then yes, it would return the value that was set all the way back in 2015.
And actually, I think all clients do support setting storage slots in Genesis if you make private, if you just make a private network. But yes, I think the question is, are storage slot persistent? And yes, they are.
So on storage slot, I have a term, maybe we could use some explanation here. In the test cases, it was mentioned that for 2929 gas cost, there are this mention of hot and cold slots. So for people who are trying to understand on a high level, what are these hot and cold slots? And also if this is for testing purpose only, or would it make any difference in practice?
So hot and cold is a concept introduced in EIP 2929. Basically, a cold storage slot is a slot that was not yet accessed in that transaction. And so it might not be in the cache. And so you charge an extra 2100 gas to account for the cost of reading it from disk. But if a storage slot was already read in a transaction, then we know that it's in the cache. And so we call it hot or warm, and we only charge an extra 100 gas to read it again.
And that's that change 2929 does not really, it's not really something which is intrinsically tied with this partial removal of refunds. I view them as two separate things.
They are, yes. So Martin, actually, how do you feel about this mitigation that I proposed, where you either charge less or you add some small refund to still create keep a little bit of incentive for non-zero to zero?
That might be doable, yes.
So
Yeah, I mean, I guess it's like a little bit ugly, but the goal is to make things better, and then state expiry is going to be the time when we make the when we can make more comprehensive reforms to all of these gas costs anyway.
Just to kind of clarify what you mean, like what the question you just had, like, so is the point of this, like, is the incentive there to avoid changing the state, basically? Because like without the second part, you won't have any.
Okay, so here's the problem, right? Let's say that you have one unit of wrapped Doge, right? Wrapped Doge is an ERC20 token on Ethereum, and so your balance of one wrapped Doge is represented as the number, like let's say wrapped Doge uses 6 decimal places for simplicity. It's just the number 1 million, right? Meaning 1.00000 is stored in a storage slot, and that storage slot is like basically a storage slot in the contract of that ERC20 contract, where the storage slot key is like the hash of your address, right? Like that's how ERC20s are implemented. Now, let's say you want to, let's say you don't like wrapped Doge today, and you just decide you're going to sell all your wrapped Doge on Uniswap. So, you make a transaction, and as part of that transaction, the wrapped Doge balance goes down from 1 million to, or the value in the storage goes down from 1 million to 0, right? 0 is your new balance. So, in the status quo, the storage slot moving from 1 million to 0 gives you a refund of 15,000. And like this is a kind of basically a bit of an incentive that you're given to do the clearing. Now, if let's say the next day you decide, oh, actually he wants to buy some wrapped Doge again, then you go on Uniswap and you buy like 1 wrapped Doge, and your balance goes back up from 0 to 1 million, right? Now, because your storage slot the next day is going up from 0 to 1 million, the storage slot is being kind of uncleared, right? And so it's a new storage slot that's being created, the storage is being expanded, and you get charged an extra 15,000 gas for this. Now, post EIP-3403, in at least the current proposed form, the incentive to clear goes away, right? So if you go from having 1 wrapped Doge to 0 wrapped Doge today, then you would have you would not get a refund, and then when you go from 0 back to 1 tomorrow, you would have to pay 22,300. Now, if instead you decide, oh, instead of selling my whole wrapped Doge, I am going to only sell 0.999999 wrapped Doge, right? And so I'm going to still have 0.000001 wrapped Doge in my account. So if you do that, then the gas post EIP-3403, the gas cost for doing the sale will be the same, But then if tomorrow you decide, you want some wraps Doge again, then you'll go up from 0.000001 up to, either 1 or 1.000001. And because you're not going from 0 to non-zero, you're going from non-zero to non-zero, the gas that you're charged tomorrow, instead of being 22,300, is only 5,000. Instead of being charged for expansion, you're only charged for modification. And so, like, the concern that people are bringing up is basically that when you sell your wraps Doge, you're absolutely certain that you're never going to want wraps Doge again. Then it doesn't matter whether you sell 0.99999 or you sell the whole token. But if you think that, maybe there's like a 20% chance I'm gonna want my wraps Doge back tomorrow, then, like, if there is even that chance, then it makes sense to leave like this one tiny sort of speck of dust behind, so that if the balance in your account does fill up again, instead of being charged the higher amount of gas for storage expansion, you're only charged the smaller amount of gas for storage modification. Does that make sense?
That makes sense. And then as like the way that I understand that, before 3403, then you could kind of go from 1 to 0 and then back for free, more or less, right? And so that was kind of
Right,
the DOS concern.
Right. Oh, so before 3403, the concern is that you could basically move one storage slot from 1 to 0 and another storage slot from 0 to 1, and you would get a refund. And so there was an incentive to just like fill up a whole bunch of storage slots with ones and use that as a battery, so that whenever you need to do some expensive thing, you can just kind of flip some of these storage slots to 0 to compensate and reduce your gas consumption. With EIP-3403, the ability to do this goes away.
So regarding your possible mitigation, I'm not sure I follow about the numbers there, because 5,000, that's not what it costs today.
It is if it's the 5,000 is if it's a cold S-store, right?
I don't think it's 5,000.
It should be. I think it's 2,900 for the S-store and then 2,100 for the cold read. But the points basically would be that, like, there is some amounts that you're being charged for the first write, and you can either charge less, or like if a storage slot goes from say 5 to 7 to 0, then like if we want to make that second thing cheaper as well, you could just do a refund. And to prevent the refund from being abusable, you could cap the refund to 5,000, and 5,000 is just like you have to pay 5,000 to modify the storage slot at some point, so you can't get more out from a storage slot than you put in.
Yeah, okay. I think we would need to get it down more detailed, because because you tripped me up a bit, because we don't, I mean, it's not 5,000, it's 2,900 plus 2,100, and they both kind of follow different routes of logic to because the second time you won't pay that 2,900.
Right. No, I think realistically it would have to be done as a refund instead of doing it as a cost reduction.
Another thought would be to raise the 19,000 to 19,900, which is the effective refund today for this 0.010 case, where we land at 212 right now, instead of 1,112.
Right, but that would not affect the token clearing issue.
Yes, it does not address the same thing. So it would be good if we sketched out that idea, possible mitigation, a bit more in detail. I think.
Sounds good.
Are there any other notable applications aside from arbitrage bots that might be impacted here?
I know there are some applications that use gas tokens. I'm not sure exactly which ones. But like it's important to keep in mind that those applications won't break. They'll just like stop being twice as cheap. Or well, it's not even twice as cheap. They'll stop being like a little bit cheaper.
And I really don't know enough about the whole application layer and DeFi layer to answer that question.
So on this particular thing, like talking about the usage of this gas token, as I understand, there is one downside of using this gas token. Like they are inherently inefficient. So can you elaborate a little bit on how it can be using other opcodes? The base fee opcode would be better than using the gas token here?
So right, I see. Okay, so well, the base fee the idea of a gas price derivative using the base fee opcode and using gas tokens, they are a bit like they can serve the same function, but they are a bit different, right? So using the base fee opcode to make a gas price derivative, that just basically means you convert some of your ETH into this financial asset, and that financial asset will be able to we'll be able to just give you the an amount of ETH that's proportionate to some amount of gas multiplied by whatever the base fee is, and that's different from the that's different from gas tokens because the base fee opcode or financial markets using the base fee opcode are purely a higher level construct. And so the gas that you're getting from basically cashing in on those derivatives, like that gas comes from other users, right? And so from the point of view of the protocol, like it doesn't, the protocol, it doesn't like see that and it doesn't kind of affect any of the protocol's invariants. And also the other thing is that no matter how much gas worth of that derivative you're claiming, it would only cost a very low amount of ETH, right? It would only cost like maybe like something like 20,000 gas to claim. Gas tokens, on the other hand, like they cost a fairly huge amount of gas overhead to claim, and they're not a higher level derivative. Like they're actually kind of tying into direct protocol rules, and so they actually do increase, say, the total amount of gas in a particular block.
Thank you for explaining that. I know it is not directly related to the proposal, but I was curious to understand that because it came up also in the base fee opcode discussion. We have almost hit the time, but because this is PEEPanEIP, I have one last question related to the status of the proposal. Irrespective of the decision made by the AllCodeF team on inclusion or not, as co-authors, do you see any more changes in the proposal to be added?
Again, I expect that we'll do one round of thinking and propose a version that keeps some degree of incentive to set things to zero. What do you think, Martin?
Yeah,
No.
I think that might make sense, probably.
Okay, cool. In that case, very well, because I was wondering if this proposal is ready to be moved into the review status, because now it is under active discussion. That makes sense. Thank you. So this was really great. I really thank Martin, Vitalik, and everyone on the call for joining us and talk about the EIP-3403, its advantage, and obviously the implication on Ethereum users. So following some of the past CodeF meetings, it seems like there is a particular group of users who are not in favor of this proposal and have some alternate proposal. So whether it is included in London or not, it's a decision to be taken by client devs and the community. But this video that has been created, it's for educational purpose. We just wanted to talk about the proposal and let people know the advantage and why devs are thinking of including them in upcoming upgrade. I hope the details shared in the presentation will help the community understand the trade-offs of accepting or rejecting the proposal. So On this note, for all our YouTube viewers, thanks for watching. If you like this episode, hit like. If you care about this proposal, do share the video with other community members and help Ethereum devs to close on London proposals. If you have any further questions that could not be answered in today's episode, you can find resources of this proposal and presentation link with the guest contact in the description section below. You can reach out to us with your questions or the guests. As always, we would love to hear feedback and improvement suggestions. Do let us know which EIP would you like to see in future episodes. Next week, we will be joined by Afri to talk about the difficulty bomb, also known as Ice Age in Ethereum. So stay tuned, keep watching, keep sharing your love with Ethereum cat herders. This is all of us signing out.
Thank you.
Thank
Bye.
you.
Thanks all.
So
Okay.